Okay. If you got my email right before class, I got a few questions on homework 6.3, and given that we're doing exam review today anyways, I thought we could take that as take a few minutes and talk about it. But at the same time, we're not talking about just that assignment. We have the entirety of shear and moment diagrams and deflections, etc., which is going to be on the exam. So I don't want to devote too much of our exam review to that one homework assignment, but we will talk about it. We're still working on grades, admittedly, a little bit of a backlog, but I know my TA had a big project in one class, and she just finished that, and now that this is the last homework assignment, the one that you turned in today, this is the last homework assignment this week, and the next week you're going to have a homework that's assigned Monday, due Friday, so she'll have a little bit of time to catch up on that. So what I'm going to do for homework 6.3 is I'm going to make it due at 5, and the solution's going to turn on at 5, and so we'll talk about a couple things that hopefully might answer some questions that you have. But let's get into the exam review. I have a couple things that I don't want to say I tweaked. I don't really think it changed anything all that much, but I'll explain. It might seem a little quirky, but you'll see why. So the exam's going to open at 9:58, and it's going to close at 10:55. So just so everybody's aware, the reason that I open it a couple minutes early is to make sure that we don't have any technical glitches and whatnot on Blackboard. And I don't have a problem with letting you test until 10:55. Like, I know class ends at 10:50, but I don't have a problem with you taking a few minutes and closing everything up. So if you add this much time, this is like 57 minutes. What happened last time is I set the timer for 60 minutes, and so Blackboard let you go a few minutes extra. And so since we have a class coming in at 11, I kind of want to make sure that we're not bumping into other folks' schedule. So the timer where it said 50, where it says 60 minutes is going to say 57 minutes. I know that seems like a little quirky, but I wanted it to encapsulate the window. But I'll tell you one thing I did the exam this morning, and I did it, and it took a little longer than I thought. So I gave you some extra data to make it go faster. And I'll go ahead and tell you, on one of the problems, I was going to not give you the support reactions, but I did the problem, and it ended up taking me longer than I wanted it to, so I gave you the reactions. So again, I'm not trying to make a time crunch exam. I'm really not. I'm not trying to do that. And I'm really not trying to test you on stuff we've already tested you on, okay? I want this to be a test on shear and moment and on beam deflections and flexural deflections, frame deflections, what we've been talking about since exam 1. All right, so I know the timer is a little weird, 57 minutes, but that's why. But it's the same, other than that, it's the same format as last time. It's once you start it, you have to complete it in one sitting. All the questions will appear at once, and it's open book, open notes. One thing that I highly suggest that you have with you is a straight edge. I really think you should bring one. I think it'll make your life a little easier in doing some of the diagrams and whatnot. So just take that for what it is. I would bring a straight edge. I have no problem with you using any of the aids on Blackboard, the lecture recordings, homework solutions, lecture notes, etc., the stuff on OneNote. The one thing I don't want you to use is another individual. That means somebody else in the class, Chegg, any of the stuff that miracled itself onto the internet. In the end, though, and I think it was statics, I told this, I said, if you are spending time in the exam trying to seek out the answer somewhere else instead of actually just doing the problem, you probably do better if you just attempted it. So 4 to 5 conceptual questions. I'll go ahead and tell you 3 computational problems. Make sure, do me a favor and type out an answer for every question. You'll see the way the questions are structured, no pun intended. It's structural analysis. But you'll see the way that they're structured, that there is sort of a discrete answer that you can put in. Let's talk about the topics. So what are we talking about? We're talking about shear and moment diagrams and deflections. Now, in one problem, like I said, in one problem, I gave you the support reactions because for that problem, I thought that it added more time to the exam. But that being said, I actually think that the skills necessary for support reactions are probably not the worst idea in the world to make sure that you're good at. Because if you can compute support reactions, it means that you can sum forces, it means that you can sum moments, and those are all the skills necessary to, write shear and moment functions, to draw shear and moment diagrams, et cetera. So I put it on there not to say that I'm directly testing you on support reactions, but just because I think those skills are valuable to what's really on the exam, which is shear and moment diagrams. So make sure that you can determine internal shears and moments at a given point. Make sure that you can formulate shear and moment functions for beams and frames, and make sure that you can construct shear and moment diagrams for beams and frames. And for deflections, make sure that you can analyze real and virtual beams and frames, and you can compute both displacements and rotations, and you can account for both axial and flexural deformations as appropriate. Here's just sort of the stuff that I think you need to know. You need to know how to deal with distributed loads, both uniformly distributed and linearly distributed. So, sort of rectangular loads and triangular loads. Make sure you can handle, the three boundary conditions that we've been dealing with this whole semester. Make sure that you can handle inclined loads. For instance, if you have a beam and you have an inclined load that only the vertical component of that load contributes to the shear diagram, right? We were talking about transverse shears, just as an example. Inclined rollers, make sure that you can handle that. And again, I don't, to be clear, I'm not going to try and get too far down the weeds of what we did on exam 1, but I just want you to be thinking about this stuff. Cutting sections through members and hinges, make sure that you know if you cut a section through a member, through an arbitrary point in a member, you can have 3 unknown internal responses: an unknown axial force, an unknown shear, and an unknown moment. But if you cut a section through a hinge, you only have an unknown axial force and an unknown shear, no moment, because we know that the internal moments at a hinge are 0. So just make sure that you know that. You know the relationship between loads, shears, and moments. I think you probably got tired of looking at this slide when we were going through shear and moment diagrams because I kept having it on all of my lectures, but everything that we were doing was built on this. Make sure that you understand the graphical approach. This is big, for shear and moment diagrams, that at any given point between your load diagram and your shear diagram, the slope of the shear diagram is equal to the load, and the change in shear is equal to the magnitude of load between 2 points. And between shear and moment, the slope of the moment diagram is equal to the shear, and the change in moment is equal to the area of the shear diagram. So kind of the same process, just staggered down. Virtual work for beam deflections. Again, I'm not going to make you do shear deformations. I just wanted you to understand it. For beams, obviously what I'm most interested in, and really with frames too, is virtual work for flexural deformations. So we're summing the integrals little m big M over EI to fully sum up the energy in the system. So little m is the virtual moment function, comes from taking all the loads off and putting a single concentrated force or moment at the point of interest with a magnitude of 1 in the direction of the assumed, or in the assumed direction of displacement. And then your big M is your moment functions from the real loads, from the actual original loads on the beam. And then E and I are your section properties. Don't forget your conversion factors. For deflections, it's 1728. For rotations, 144 times 180 over pi to get that into degrees. And that's it. That is pretty much everything that you need to negotiate exam 2. So I'm going to stop for a sec. I will happily entertain some discussion on homework 6.3, and I have some things I want to discuss with that to maybe make that a little easier for you if you want to resubmit. But before we do that, any general questions or anything that you're thinking about that comes to mind? Okay, you, then you.
For the shear moment diagrams, how's that going to work with the blackboard?
All I can say is when you read the question, those types of questions will ask a particular, like I might ask you for a value or ask you, something about it, and you'll understand what I mean. But I'll be grading your shear and moment diagram based on the scratch computations, yes. Which is one of the reasons why I say if you need to draw a shear and moment diagram, please bring a straight edge. It's going to make your life a lot easier. Just trust me on that. Okay. You'll. All I can say is you'll see what I mean. That's all I can say. Oh, there's got to be more questions than that. Tell you what, do you want?
Ready for 6.3?
You want me to talk about 6.3 for a second? Okay, let me talk about 6.3 for a second. All right. I brought my book with me today. What was that? 740?
Yep.
740. Okay, hold on. Okay. All right. So, a couple of things about this assignment. Let's start off with the virtual structure, because if you read the assignment, that was what I wanted you to start with, was the virtual structure first, and there was a reason for that, okay? So here's the structure, and I'm just going to draw it as lines. I'm not going to add the beam depth and whatnot. Okay. Okay, and let me put some labels on this. So this is A, and then like point B is right here. This is D, this is C, and this is E. Now remind me, what was the goal in the problem? What were we trying to do? Horizontal deflection at E, okay? So what that means is this. You place a single horizontal load at E. That's it, okay? Nothing else, all right? I placed it to the right because if you look at the original structure, there's this like 40 kip load pushing to the right. And so if I look at the structure, I kind of think that point E is going to slide this way. Remember, this is a roller. A roller allows lateral translation. With me so far? Okay. Now, all right, I think a couple questions I got were maybe getting a little confused about the support reactions. Look, we have one to the right, which means that this reaction here is one to the left, okay? That's easy, okay? But a lot of folks were looking at it and thinking, well, the vertical reactions are zero, okay? Because there's no vertical loads. And if you think that, I want you to take your hand and do that, okay? Because that's not correct, okay? What is correct is that the sum of those reactions are zero. That does not mean that they both are zero. If I have 20 kips up and 20 kips down, the sum of those are zero, but it doesn't mean they're both zero. Does that make sense? Okay, so what you need to do is respect the equations of equilibrium, okay? This dimension here is 8 feet. This dimension here is 16 feet. And this dimension here, 16 feet. So if you sum moments at A, what do you have, okay? If I sum moments at A, I have 1 times a moment arm of 16 feet, right? So I have 1 times 16 generating moment this way, right? Now, if I just said those reactions were zero, there's nothing contributing moment the other way. If I'm summing moments at A, and this is contributing moment this way, what has to contribute moment the opposite direction? EY. It's got to go up like that. So EY is acting this way. So this is EY. And it also is at a moment arm of 16 feet. So EY is 1 up. And if that's EY, That's AY. Okay? That satisfies static equilibrium because that is a system of forces that satisfies the conditions that the sum of the forces in the x direction are 0, the sum of the forces in the y direction are 0, and the sum of moments are 0. Going back to engineering 213 land, what we have here is a system of two force couples, right? We have two forces equal in opposite directions separated by a moment arm, right? We have 1 times 16 going this way, and we have 1 times 16 going the other way. Bringing it back to engineering 213 land, right? That's what's going on here, okay? Now, does that make sense? All right. Now, the other hint I mentioned on the homework assignment is that your coordinate systems should be pointing towards D. And what I was saying about that is I was getting at this, okay? Typically what you don't want to do is define a coordinate system in the middle of the member, because if you're cutting sections and you're cutting that piece out, you need to know the internal shears and axial forces and whatnot there. Typically what you want to do is define your coordinate systems at the end, right? Because if I start here, there's nothing down, there's nothing past it, right? Does that make sense? Now, what is the internal moment in this member? 0. There's nothing here, right? So what I'm getting at is for this member, the little m is 0. And if the little m is 0, what's the deal with the big M? Who cares what the big M was? This is why I wanted you to do the virtual structure first, is that if you look at the virtual structure, there's a 30 kip load right here on the free end at point C. And so, yeah, you're going to get a real moment. But it doesn't affect the horizontal displacement because there's no virtual moment there. So just don't worry about it, okay? Does that make sense? All right, so if we wanted to use the whiteboard maybe to log some of our functions here, so MCD is 0. Does that make sense? And then for this vertical member and this horizontal member, we can take this whichever order we'd like. Let's take the vertical member. So here's our support condition right there. We had this, 1.0, right? This is the origin of our coordinate system, and I'm cutting a section right there. So what's this distance right here? X, right? It's x1. Just, x. You can think of it as x. I'm just labeling it so that we know what we're talking about. But yeah, it's x1. And there is an internal moment in this member. We'll call it AD. What is MAD? It's x, right? Because I have 1 times x going this way. I got to have 1 times x going the other way. So, MAD is x1. Valid from where to where? No. 0 to 16. Right? Because it's along the length of this member. And the member, this is the x coordinate. This is x equals 0, x equals 1, x equals 2, x equals 3, x equals 4. This is up to the top, x equals 16. Does that make sense? If it doesn't, raise your hand and tell me, because I want to understand. Now, to be clear, for the real structure, we're going to have to do something a little different for this member. We'll deal with that later, okay? With me so far? Okay. What about member DE? Now, I'm not going to do the whole problem for you. Some of this I'm going to have to stop. So what did Dr. Mike's tips and tricks say? You cut a section and you look towards the origin, right? Cut a section, look this way because that's the origin over there at E. And again, all I care about is MDE. What's this distance right here? How long is this section? X2. So what's that M function? What's that little M function right there? X2, right? So M, we'll call it ED since we started E and go to D. What's the range of applicability? 0 to 16. Does everybody see that? Because I'm going from here to here.
Oh, yeah, sorry.
No, that's why we're doing this. Does this make sense? These are the virtual moment functions that fully define the structure. Does that make sense? All right.
So would you have 4 cuts on your wheel structure instead of 3?
We're getting to that. Don't worry. We'll get there. Yes?
If you made 3 virtual functions, or say 2 for that bottom beam, would that give you an incorrect answer?
What?
Well, you know, it's the same. It depends, because, well, you get the same value for it. The value of it 0 to 8 and 16. I split it into 2, but I counted the whole length.
Let me show you what I'm talking about here in a second, okay? You'll bear with me.
It just helped me make it make sense for the wheel structure.
Well, just bear with me. Just bear with me. Oh, I got too far. This is what, 3 kips per foot? This is 40 kips. And this is okay? With me so far? Now, hold on for a sec. Before we start doing some hullabaloo, let's look at this. Let's make sure we're all on the same page. How many moment functions for this member? 1. But it doesn't matter because the virtual moment is 0, right? So over here on this board, what we'll do is we'll say that the deflection at E equals, okay? Okay? And what we'll do is we'll say something like 0 to 8 of MCD over EI. But it doesn't matter because it's going to go to 0, right? We're not done because we got other stuff we got to add to it. But with me so far? So let me group this so it's kind of a little easier to see. So here's this, that. We got other stuff we got to add to it. With me so far? All right. Now, what I want to do is focus on this column. So, but before I do, let's put some dimensions on this. So, okay. Now, does somebody have some reactions for me, or do we need to do this together? Like, I could tell you that this reaction here is 40 kips. What about the vertical reactions? 49, 29. Okay. Wait, this is 49? Okay. Oh, one other thing. This was I, this was 2I, and this was 2I. Why am I doing that? It's like I'm Roman numerals. So is that fair? Okay. All right. Let's look at this for a second, because this is the money. This is what we're trying to do, right? So how many moment functions are we going to need for the real structure to fully define this, for this member? Let me ask again. How many real moment functions are we going to need to define the moments along this member? One, right? So if we're finding out this deflection right here, so delta E equals this integral, but it's 0, plus, oh, I got to put my integral there. And it's 2I. It's x2, right? What are the limits of the integration? 0 to 16. Okay, does that make sense? Okay, now let's pay attention for a second. How many moment functions, real moment functions, am I going to need to define the moments along this member? 2. Where's our origin? Where did we define our origin before? We defined it at A, right? So this is x1, this is x2, and what the heck, let's put x3 here, even though we don't use it. So the way that this has got to set up is I've got to have plus, I'm running out of room here, so I'm going to have one integral from 0 to 8 and another integral from 8 to 16. Does that make sense? But, all right, so what are we integrating? Okay, so let's see if we can fill this in. Both of these are going to be integrated with respect to x1, right? Fair statement? Both of these have the same stiffness, right? Here's the kicker. I'm going to have different real moment functions, right? But I'm going to have the same virtual moment function. Because look at the range of applicability. I'm going to have one of these from 0 to 8, one of these from 8 to 16, but this is valid for that whole range. Does that make sense? Okay? And when this is all said and done, this whole thing for units, right? Should you want me to like headbang next to it so you can TikTok it? Or?
Yes. Yes, please.
Yeah, I'm not doing that.
Would that go back in and change our submission?
Yeah, with all homework assignments, you can upload 100 billion times as you want. I'd grade the last one. That's why I extended the deadline.
So when you do the real moment function for BE, how would you?
Well, all right, let's do that. And I ain't doing any more. Watch. So I propose we need to cut how many sections? 2, right? All right. So we need to cut one section about like that, and we need to cut one section about like that. Is that a fair statement? So let's do that. And which way are we going to look when we cut these sections? We're going to cut these sections and look which way? Towards the origin. We're looking down, right? That's the origin. We got to look down because we got to, well, I guess we don't have to, but we have to make sure that we're referencing the same coordinate system so that these are apples to apples. So, section 1, wait, that's a short one, is just like this. This was 49. This is 40. What is this dimension right here? X1. And I'm looking for this right here, MAD. It's going to be MAD1 because there's 2 of them, right? Is everybody with me on this? This is important, you know. You got a celebration in a couple days. Everybody with me? So what's MAD? 40x. Okay, so let's put this right here. MAD 1. What's the range? So far, so good? What's so funny? Let me in on the joke.
I'll tell you later.
Not appropriate for a recording, I guess.
Not to go with the
Oh my goodness. All right. Section 2.2. Cut a section, look down. When I samurai sword or lightsaber through line 2.2 and look down, what do I see? I see this. Right? Okay. Let me drag this down a little bit. I'm interested in finding this. Now, help me out. What is that dimension right there? X. That's x1. It's because it's the same coordinate system. Right? We're doing this with respect to this coordinate system. X2 is going this way. Right? What is this distance right here? 8. So what is this distance right here? There you go. So what do I have? I have MAD2, right? I do that right? Going this way. What is this? 40. We're cutting at the cut. 40 times the moment arm of what? X1 minus 8. And then we have what? 40 X1. Is that fair? So 40 X1 equals MAD2 plus right? Drag both sides over. I can cancel that, and I get 320 equals MAD2. Did anybody try and actually draw the moment diagram for that member? Did you try that? Well, what would have happened if you had is you would have found wait, let's go the other way. This is 8 feet, 8 feet. The shear diagram goes over 40, up, over. And then the moment diagram is a line from 0 to what? 320, and then a constant moment of 320. A constant moment of 320. And then there's a concentrated moment there if you cut a section, bring it back to 0. You know I'm putting this in the notebook, right? So over here, watch this. So over here, what do we have? 40x1 here, 320. But both of them have the same virtual function. I'm not doing that one. You can do that one on your own. I've done enough already. I can tell you that this real moment function's a little long. There's like an x squared term and a constant and all sorts of stuff.
I left mine in the form for the BD, H16. I left it in the form from 40x minus 40 minus x minus 8.
And if you carried that out, you'd got 320. Yeah. I mean, you probably don't get the, here's the thing, you probably got the right answer. But what I'm trying to do is show you that there's a connection, that there's connective tissue between this and this. Now, after all this hullabaloo discussion about 6.3 with 10 minutes to go, how do you feel about the exam? Better? Okay.
I feel comfortable with everything except for the deflections, because that's what happened with the first exam. I felt comfortable with everything except for the deflections that I got the last problem.
Okay. I can tell you, I believe the way the exam is set up, there is very little repetition. I really don't like you having to do the same problem over and over and over again. And I can't tell you what the problems look like, because then I'd be telling you what's on the exam. But what I can say is they're not designed to be time critical. The exam's not designed for you to sit there and have to do the problems over and over and over and over again. You know what I mean? And I also think that some of the time savings are maybe a bit more obvious on this exam than they were on the last one. For example, remember the real structure, the real truss and the virtual truss, how they were the same truss and you could just divide the answers? You know, it's a little more obvious on this one. So, a little more obvious. I think that the exam's pretty straightforward. I do. So, but we still got 10 minutes. I want to stop talking, open the floor to you. Any more questions?
Just to clarify, so in this case, we can factor out that E2I.
Oh, yeah.
Since all three of those are the same
You're right. See, because this one went to 0, they're all 2i. If this one had terms to it, you couldn't really do that. Well, what you maybe could factor out the I, but you can't forget the 2's. You know what I mean? You can factor out the E. I got no problem with that. I write it this way because this way works if the EIs are common or if they're not common. Do you know what I mean? So, but yes, you can factor out. In this case, what you could do is say E2I, and you could say boom, boom, boom. You could easily do that. And then this is all 0 anyways. So like that's what you got to do to determine the deflection. And so like these two are already figured out. All you got to do, we know this one is x2 because we figured that out. Now y'all got to just do that. It's not hard. I'll go ahead and tell you also my solution to homework 6.2 is really long. Like it's like 8 pages long, but I have a lot of writing where I'm trying to explain what I'm doing. And in complete fairness, you might have done the problem differently than I did, and you still might have gotten the right answer. So that's okay.
For the use of symmetry on any of these kinds of problems, it just has to be the same loading on each, like from the midpoint, it has to be the same loading on each side. You can use symmetry.
So yeah, admittedly, symmetry is it's a tough one to use for problems like this. It's not going to work, but you have to have symmetry with respect to the geometry. So like a simply supported beam or something like that, you have to have symmetry with respect to the loads. You have to have symmetry with respect to the stiffness, right? You also have to have symmetry with respect to the point of interest. So you like a simply supported beam, uniformly distributed load, I want the deflection at midspan. Then what you can do is define a function from 0 to L over 2, integrate, multiply by 2. Then you can do that. And I mention that because that's a lot of time, like, let me be clear. This is a course on structural analysis, so I'm trying to give you intricate, challenging problems so that you understand the concepts. But in steel design, we deal with a lot of simply supported beams, uniformly distributed loads, right? This beam is simply supported, uniformly distributed, right? Like that's real world. I'm not saying that you don't deal with complex structures in the real world. Of course you do, but you do a lot of routine structural analysis too. In fact, one of the very last things that we'll do probably after Thanksgiving in that last week is I'm going to have you derive stuff like this. Like here's a beam, here's this, and instead of telling you the load is like 2.5 kips per foot, I'm going to say it's W. And I'm going to say that this is L. And I'm going to say, tell me what the maximum moment is as a function of W and L. And there is a reason I'm doing that. I'm not just trying to be a jerk and throw alphabet soup at you. It's because open up the steel manual. Go to the NDS, go to ACI, and they have these analysis aids that you as engineers can use. So it's like if you have this case, it'll tell you that the maximum moment is WL squared over 8. And I want you to know, like, where'd that come from? Well, this is WL over 2. This is WL over 2, right? So shear diagram, up, bam, bam. That's L over 2. That's WL over 2. So that area is WL squared over 8, right? So, whoop, whoop, And that form, like WL squared over 8, if you take concrete design, you use that a lot, but it comes from this, so. Oh, there's got to be a few more questions burning in the back of your cerebellums. Yes, sir.
Would there be any Excel requirements?
No, that's a great question. There's no Excel on this exam. I mean, I guess you could maybe like set up your integrals in Excel and like sum it that way, I genuinely think it would be more work than just doing it. Now,
when you do the shear moment diagram,
what about
for the Excel?
like what we did with the triangular load? No, none of that. We don't have. You won't need that. Like in all honesty, I'm not telling you no, but I'm telling you it would genuinely take way more time than just doing it. Now, I'll tell you on the third exam, I am toying with not just some Excel work, but some mass stand work on the exam. So I haven't made up my mind yet, but you haven't used mass stand yet, so you don't know what I'm talking about. So that's next week. Which, by the way, if you haven't installed mass stand on your machines, do it. We're using it on Monday. We have a pretty interactive exercise on Monday and Wednesday, so I need mass stand installed. Three minutes. Any questions?
Is it okay to use this calculator, or do you have to use this?
That's fine. That's fine. I don't care what calculator you use as long as it doesn't have a Wi-Fi connection. I mean, and the math that we need to do on this exam is basic algebra, basic arithmetic, and definite integration. And that calculator will do it just like that one will. So there's no features on that calculator that are really going to give you an edge.
I find it easier to see it.
That's fine. There is something to be said about comfort. You know what I mean? Like I drive a Toyota, and if I ever rent a car and it's like a Volkswagen, it's like I know how to drive, but it's not my car. Do you know what I mean?
I've had a rental for 6 months.
What's that?
I've had a rental for 6 months. I know what you mean.
Oh, Lord.
I'm not comfortable with it, though.
Oh, there's a story there. I'm just going to, I'll let that one go. Any other questions? We're going to start at 10:58. Sorry, 9:58. In here. Have your laptops. Have them charged, or bring your, adapters. I'll bring the party favors. Bring a straight edge. And I'll see you on Friday.